we're honored that we have Dr. Arianna Gleason with us today from SLAC National Accelerator Laboratory. Dr. Gleason is a senior staff scientist and deputy director of the High Energy Density Science Division in the Energy Sciences Directorate at SLAC. And she's also an adjunct faculty in the Dorr School of Sustainability at the Department of Earth and Planetary Sciences at Stanford University. Dr. Gleason earned her PhD from University of California in Berkeley, and she worked on high pressure mineral physics and planetary sciences. Her research spans geo and planetary science to inertial fusion energy science, applying ultra-fast X-ray probes to study dynamic material processes. She has received several major honors, including the DOE Early Career Award, the DOE Oppenheimer Science and Energy Leadership Program Fellowship, the Presidential Early Career Award for Scientists and Engineers, and she recently became a fellow of the Mineralogical Society of America. And her talk's title is Harnessing Star Power on Earth through Artificial Intelligence. We're very grateful, Dr. Gleason, and thank you for joining us with such short notice. I would like to hand this over to you, and Chad, if you have any questions, please write it down and I'll read it while her talk is over. Thank you for that.
Great. Thank you so much. I really appreciate that introduction and the kind invitation to speak to you all today. It's really my great honor to be sharing with you the excitement within the fusion community, in particular in inertial fusion energy. And I thought that today, in this context of Fusion Week and recent excitement from the Department of Energy in launching this new Genesis platform for artificial intelligence advancements, I would try to bring both of those pieces together. And so that's the perspective I share with you today and how we can harness star power here on Earth. And I'm not going to beat around the bush, a shameless plug for a workshop that's coming up. So please save the date. We are really excited to have a new opportunity to share our thinking in advancement of inertial fusion energy here at SLAC, and leveraging our really unique capabilities, which I'm going to talk about as well, some of the facilities here at SLAC. So this is an IFE at SLAC workshop. It's in August. Anyone is welcome. There'll be a small registration fee, but we have a lot of opportunities for folks to attend, also without cost, supply, travel support, and the like. So if you have interest, there's no QR code yet. We don't yet have a website set up, but we're still in the planning stages. But please mark it on your calendar, end of August, August 24. Happy to support travel. Please reach out. Students, postdocs, technicians, engineers, faculty, private industry in particular. We are really looking for their input. So again, I'll circle back to this advertisement, but in the spirit of Fusion Week and launching critical discussions and building consensus, we are going to be holding this workshop. Okay, but turning our attention to how to leverage, how to bring into our sphere of fusion science and technology the advancement opportunity with artificial intelligence. And this is sort of the value proposition I lay at your footsteps for us to consider. It's that with AI and AI agents, this so-called agentic AI, that we can accelerate, in particular, inertial fusion energy designs. And I think we're already doing this, sort of nibbling around the edges in different communities, but having a larger scale community planning and thought toward how we're leveraging surrogate models, moving towards true digital twins for many of our notional ideas for a future pilot plant that is based on an inertial fusion concept. This is going to be not only our future, certainly we need to lean in and embrace it, but for the early career scientists and students in attendance, really being excited. Like this is going to be what happens in your lifetime, certainly. And I really think you will be the first ones to flip a switch in leveraging fusion energy powered from the grid. So it's really an exciting time. And I sort of was thinking about, in particular, for inertial fusion energy, and we'll do a zoom out and talk about the science and technology required for all different types of fusion. But right now, in particular, for inertial fusion energy, which is sort of the launch point for certainly the RISE Hub, the focus of this seminar as one of the now named US IFE hubs for inertial fusion energy. There's sort of a progression here that, first of all, we now see that ignition is really possible from the watershed moment in 2022 on the NIF when we achieved scientific break even, right? A gain greater than one, more energy out than put in. And now we're leveraging all the good science and technology across multi-scale, right? So across length and time scales, looking at the physics that's required and saying, okay, let's take a physics experiment that was the NIF results and let's point it at developing commercial fusion. Our understanding that in order to make this energy efficient, right, to have a concept that really delivers energy to the grid in a reliable and robust way, it means we are in a high rep rate paradigm. In other words, this is not a shot every 12 hours, right, like is on the current NIF architecture, but we're talking about hertz. So that means multiple hertz capabilities in our technology, and that presents a new data paradigm. And here enters AI for helping us to not just collect that data, but the diagnostics that monitor the various components of that reactor. Of the plant and feed that back to us. It means we need detectors that have real-time capability, so-called compute at the edge, and an ability to make decisions faster than any human can, right? And so here's a fun fact. It turns out like for us to blink, okay, so everybody on the call, like blink your eyes. That's around like 300 milliseconds or so for us to blink our eyes. But we need a latency response. We need an ability to make a decision about any given diagnostic and therefore control of aspects of our power plant in less than 1 millisecond, right? So our ability as humans to be in the loop is going to be sort of detrimental. So we need to lean in and call upon our strategies with artificial intelligence and agentic AI, I think, to help us with a variety of aspects. I name a few here, our targetry, our beam steering, and how we make decisions. And then I think there's a whole portfolio. Number 5 here is really close to my heart. A lot of the science that I do within the RISE Hub with many partners here on the call, BYU, Colorado State, our industrial partners, is focused on making the targets better, making the targets correct, not only to get the physics right, but then how do we scale, right? And that is so critically important because without our fuel, right, the material or the actual DT itself, there is no fusion, right? So I think we're in an exciting time to launch this forward. And so we are looking toward our leadership here in the US. In particular, there was a new initiative. In fact, it was an executive order back in 2025, towards the end of 2025, called the Genesis Mission. And this was a DOE initiative that calls upon all of the national laboratories, private industry, academia, to think up what are your best and brightest ideas around not just using AI, but designing next generation AI models so that we can point these tools and capabilities at the most important and challenging problems of our time. So it is led by the Department of Energy. Therefore, our national laboratory DOE ecosystem, all 17 national labs are engaged. And recently, proposals were submitted, and they are currently being reviewed. But it's really a sort of once in a lifetime opportunity. It's being thought of as our current era Manhattan Project, right? The level of funding is not quite on par. It's around $300 million as um, put together from existing programs within DOE. So there was no new FY26 funding. Maybe there will be FY27 funding. We're not sure. But essentially, there were 26 so-called lighthouse or notional priority areas, of which fusion had its place in those various lists. And the idea is to leverage our nation's supercomputing, our different AI models, and the data. So here's another theme of my talk is that artificial intelligence, yes, of course, but garbage in, garbage out, right? So part of our role, in particular within the RISE Hub and focused on inertial fusion energy, is to provide that critical benchmarking data, right? So still humans in the loop, still doing critical experiments that test hypotheses that are being fed to us or considered from our current physics models, in particular, the performance of the capsule and the capsule materials. Okay, so yes, foundational models, but we definitely need those critical data. Quantum systems, and then scientific instrumentation. And here's another piece where within the US IFE ecosystem, incredible facilities domestically here, yes, but actually internationally leveraging third and fourth generation light sources, mid to large scale laser facilities, in particular leveraging LaserNet US. So that's another theme. And finally, just to say, this will really it's really our pull, I think, for the U.S. to set an agenda in AI that is not just compelling but meets the challenges of the day, in particular in energy, right? So we will see in just a moment a few other view graphs where AI is not only powerful, but AI itself to operate it requires an incredible energy need. And so here is a unique opportunity for fusion to be the AI energy, right? So actually sort of turning this problem on its head in this community for fusion and saying, you know, we can leverage a lot of our innovation and point it at what's required for data centers. And so here's a graph. You guys, it's probably a bit out of date now, but the energy demands, in particular, as we push and innovate more in agentic AI for many different aspects of industry and just daily life, right? The energy consumption and demands will probably go up by at least factors of 20 to 50%. Here's you know, a whole suite of different industries, and the projection by 2050 is certainly not to level off, but to continue to increase. And in particular, if we look at the different production, so here's a graph of energy production, just holistically, the many different types of energy. You know, we see that artificial intelligence is really going to be taking the lion's share as not just in 2025, 26, but going forward. And so we can think about the different types of, you know, sources, whether it's fossil fuels, nuclear, hydro. And you can see that, you know, fossil fuels are going to be continuing to have limitations. Natural gas is another possibility, but there's a trade space of what is most resilient and available to us domestically, so on and so forth. And we see that actually fusion energy, nuclear energy, is well positioned to not just be abundant, but also safe and have strong positives in terms of long-lived nuclear waste. being mitigated over traditional fission-based. I want to highlight that there's a real opportunity here for fusion in particular to be that solution for what's required for AI energy, and is also being considered quite a bit between public-private partnerships, even now going forward. And so here I launch into fusion. So the closest thing we have to a working fusion pilot plant is a plant, not even a pilot plant, but just a full-on plant is our nearest star, is our sun. And so we can all look up at the sun. Okay, don't do it just with your eyeballs open, right? Like certainly have protective. Don't look directly at the sun, but it is such a challenge to bring that capability here to Earth, in part because we don't have a mechanism to leverage fusion and sustain plasma burn under gravitational forces, and that's what the sun is using. Is that it uses its own gravity to sustain that. And you could think of this in the context of the densities and the temperatures required for fusion, for atoms to fuse together. And there's a tremendous barrier. And you could think about our own day-to-day experience when you have a gas that is confined. Here is a cute cartoon of helium gas in a balloon, but I also recall my own days back in Tucson, Arizona. It was very hot, triple digits in the summer, right? And I had some Diet Coke can in my car at one point and left it in the car too long. And of course, it exploded, right? And so it becomes harder and harder to contain that gas. In that case, the CO2 and in the soda. But here, the helium gas, you cannot contain that as temperature increases. And this is exactly the scientific challenge that we find ourselves in here on Earth. And the secret sauce, what is that allows us to generate sustained energy, and it's really comes down to the fuel source. And so we're talking about deuterium tritium. So I gave this talk at the National Science Bowl just recently, which is a fantastic event, by the way, for high school and middle school students. And I asked like, how many isotopes of hydrogen are there? Right? Okay, so there's three, of which we're talking about two here. So deuterium and tritium. And the idea is really at the heart of Einstein's E equals mc squared. So there's more energy out than in. We fuse deuterium and tritium together, and the output is helium and a very energetic neutron, 14 MeV. And it's that reaction and the energy released that would be the workhorse of a fusion-based energy plant. And so here's another way to look at it. There's not just an energy difference, but a difference in mass, and it's that energy out that is then converted into heating a blanket, another component of our reactor. That heat then is harnessed to essentially boil water, right? We boil water, we spin turbines, we can supply power to the grid. And so it's actually a really beautiful and simple concept. But there's a lot of technology that needs to be developed in order to do that in a financially efficient or effective way. And there's a lot of underpinning foundational physics that still needs to be de-risked or determined. And that's where you all, as our current and next generation fusioneers, come into play. There are different concepts, though, for what is the best fuel. Many companies, many thought leaders are rallied around deuterium tritium because this reactivity or sort of cross section, if you will, as a function of temperature, sort of bang for your buck. DT is the highest. But there are other opportunities with DD fusion or D helium 3. There are even other more novel ideas, but the idea is that the temperature required to actually do this is 1,000,000 times hotter than lava. So a question I asked the high school students, how many have been? I haven't actually ever been to an active volcano, but my understanding, my planetary science background, it is ridiculously hot, right? And we're not even talking about that kind of high temperature. We're talking about a million times hotter. And so the value proposition, though, if we can figure this out, here's a cute comparative graphic where if we can figure this out, a pound, right? So that's not that much. A pound of deuterium tritium fuel is the equivalent to 5,000 barrels of oil and oil right now, right? Gas. Oh my gosh, it's so expensive. Oh my God, when I filled up my car the other day. Good grief. So that is an incredible value proposition, or millions, about 3.5 million pounds of coal. So the value proposition, again, a pound, right? Anybody can lift a pound of something. And so that is just tremendous. Another cute comparative energy conversion I like to think of is the Big Mac energy metric. And so, I love food. And so thinking of how much energy is in a Big Mac is something like 10 joules per gram. And the equivalent amount of the DT fuel energy released is 34 million Big Macs. So it's just mind-boggling. And so you see that the community can get really excited around how much energy is possible, right? So the abundance, it's non-polluting, meaning the cycle, the power plant emissions is extremely low profile in terms of or negligent not that much in terms of fossil fuels released. Of course, safety wise, it cannot become a runaway chain reaction. If you don't want the process to continue, you simply turn off the laser, right? So it's very straightforward. There aren't these issues of chain reaction that maybe traditional fission based power plants are where that is a possibility. And high level waste, right? The components that we're talking about here, transuranic waste profile simply does not exist, where the half-life of some of the materials in traditional nuclear energy plants is maybe a million years. Our half-life of some of the tritium or the byproducts in the fuel cycle, maybe 100 years. Okay, so 100 years is still a long time, but 100 to a million, okay, that's a big difference. So our ability to store and understand the fuel cycle is also putting us as a fusion community in a really exciting path. And so there are different ways to achieve fusion. I'm sure we all know this, but just to sort of hold it all together and then be able to overlay how we see AI as advancing critical technologies and physics, we know there are three basic ways. So there's the sun, gravitational confinement, and then here on Earth we pursue both magnetic confinement and inertial confinement. And we can think of the sort of trade space here in these two dominant spaces, inertial versus magnetic. Magnetic confinement, it's sort of low and slow. It's a temperature or magnets that are used to confine that plasma. And you could think of it more like a furnace or a boiler. You sort of turn it on, you let it cook, and it stays. The requirement there is a larger volume and sustained over longer periods of time, right? Versus inertial confinement, where we here in the RISE hub and many of the other inertial fusion US IFE hubs, we're focused on this sort of car engine approach where it's quick and fast. You think of a car and the pistons moving, and the time scale and the repetition rate is sort of similar paradigm as what we're thinking of Hertz rate or of that time scale, the ignition and burning of the plasma based on different driver technologies. And so, what do we need in order to kick this off? This is talked about in other lectures, but there's a sort of the notion of a fusion triple product, and that we want to maximize this. So, if any of you enjoy camping, I know I do. When you go camping, you don't just and you want to have a campfire. Okay, you don't just take one stick and put it in your fire pit, and then that's it, assuming it will be sustained over a long period of time. You need to actually collect your sticks or your wood, right? Your fuel, and you need to consolidate it in a given small space. And so that's this notion of fusion fuel density. You need to bring it together over a particular period of time. That's the N. Temperature, right? You need to kickstart, you need a way to ignite initially. And this for fusion is the high temperatures. In our case, certainly also high density. And then we need a confinement time. We need to have a particular space and a duration over which that takes place. So that's this confinement time. And the idea for any kind of concept, any private company, any studies is to understand and optimize, maximize this NT tau. And we were able to here on Earth. We did this back in 2022 for the first time at the NIF, the National Ignition Facility. And it was really a watershed moment, lots of publicity. So many of us here in the fusion community, in actually a wide variety of communities, material science, certainly in energy, in technology, in detectors. We were all so just thrilled to understand the effort and the accomplishment of achieving ignition for the very first time. And the for 3 nanoseconds, right? So not for very long. We actually achieved conditions even hotter than the sun. And these are temperatures, right? Sort of 140 million degrees. So that's even hotter than the center of our sun. Peak pressures of order, many times, a billion times that of the deepest part of our planet, where the overburden pressure and the Mariana Trench, that's our highest pressure point here on the Earth's surface. But we surpassed that upwards of 500 gigabar. And we produced as much fusion energy in those 3 nanoseconds. Oh my gosh, as we humans produced in 2022. So it's a tremendous achievement, but this is something, like I said in the beginning, it's a physics experiment. The facility that's being used, of course, the NIF, we'll get to that in a second, is tremendous. But there's so much room for, improvements in terms of how we leverage this achievement for commercial fusion energy and thinking about all the different trade space in science and technology that we need to pull forward. But just to give you a sense, for those of you who haven't been to the National Ignition Facility, it's about 3 football fields. And you deliver onto a small capsule. It's about the size think of a peppercorn, 2, 3 millimeter diameter small sphere that holds deuterium, tritium, often, or I think in this case, as a ice. And 192 lasers are all pointed right at that small peppercorn fuel pellet. And it's really a fantastic facility. Okay, here's an overlay. Okay, the Raiders are not in Oakland anymore, and I feel sad. But it's about the size of 3 football fields. If you are ever in town here in Northern California, please, let me know. Let other colleagues know. There are tours. It's an incredible facility, and if you want, I won't play it now, but there's a YouTube where you can go check out really what it takes to operate the NIF, and really fantastic science that's come out. And so it sparked so much interest, not just within our own Department of Energy, of course, but certainly in commercial fusion energy opportunities and concepts that would leverage this ignition to put forward new pathways toward commercializing fusion energy. So as a take home, right? So where are we? We know that fusion works, right? The sun does it all the time. Really hard to do it here on Earth, but we see there's a pathway. Benefits to fusion, it's clean, right? Or it's and it's an opportunity to be one of the cleanest and most resilient and domestic energy producers that would be possible. There's an abundance of the fuel, compared to traditional fossil fuels, fusion, deuterium, tritium. In fact, fun fact here, in a tablespoon of seawater, there's already enough deuterium. So tritium is separate, but there's already enough deuterium to power a city like Chicago or a city like San Francisco for 24 hours. A tablespoon. That's incredible. Okay. So we have an abundance of fuel. Tritium we can handle by breeding. There are aspects of the fuel cycle and having enough tritium that for a given power plant can be sustained. And we know that it's safer in the context of if you don't want it to happen anymore, you just turn the laser off. Okay, but there's a lot of opportunities going forward and needs in order to advance the science and technology. And this is where the Department of Energy really leaned in and launched a bold decadal vision a few years ago and said, what we're going to do is we're going to help with partnerships between public institutions, meaning the DOE ecosystem of national laboratories, academia, and private industry, and map out a plan for how are we going to achieve this fusion pilot plant in sort of the 2030, 2040 timescale. And so there's been a real fantastic and exciting acceleration of private industry. And here's a quick graph, little fuzzy, I apologize, but it turns out that many concepts and private companies blossomed in that time period. And actually, to date, I think there are a number of, in particular, inertial fusion energy companies that have raised over $100 million, right? Globally, I think in fusion private industry, it's something like 15 billion right now. So that's both MFE and IFE together. I think MFE funding, private funding dominates, right? But IFE's certainly coming along. There are a lot of incredible companies that are pushing towards a first of a kind power plant. And we see that strong partnerships between our IFE ecosystem is really pulling this forward. And as I said, the U.S. is supportive of this in particular. Even in the Genesis call and under our new Deputy Secretary, Dario Gil, has indicated that fusion is one of his priorities, seen that happen. But we have a strong competition internationally, right? So here's another piece to be thinking of that fusion is, in fact, a race, right? And so whoever gets there first to achieve commercial fusion in a pilot plant construction, whoever gets there first really will change global economics, full stop. And so it is critical that we understand that landscape of non-like-minded nations that are also pushing toward fusion. And so everything we can do, all of the best minds pushing toward this and leveraging everything we can, in particular now, artificial intelligence, to solve science and technology gaps and bolster our commercial energy partners. Because let's be clear, the Department of Energy, right? Our public money, our tax dollars, I pay a lot in taxes. Oh my gosh, right? So that we are not going to build a fusion plant, right? It will be the commercial sector, private industry that will build the first plant. And so enabling this is really critical. And I think the Department of Energy has really tried to push in that direction. And to that point, we want to understand what success looks like. And so here's sort of a really complicated graph on the left. I apologize, but it's a graph looking at all the different kinds of facilities and technologies, both MFE and IFE, so magnetic fusion energy and inertial fusion energy, cast on the same plot. And this is sort of think of the y-axis here that is incredibly long, is sort of an energy density, right? How close are you getting to get to ignition in a sense, or achieving ignition here for the NIF as a function of time? As you see all these different kinds of facilities and concepts from MFE to IFE, and you see that NIF is really here at the forefront. And in that 2022 achievement, and since then, right, it's not just one and done, but now the NIF has repeated this and each time improved their gain or their break even, right? So think of a critical way to monitor success as this quotient, this ratio of fusion power to heating power, or how much energy in versus energy out. And we achieved scientific break even here on the NIF. I say here because Livermore National Lab is not too far away from SLAC. But on the NIF, we achieved that. What we haven't achieved is engineering break even, and that's using lasers as our shock driver, or excuse me, as our driver. On the magnetic fusion side, many companies and concepts are getting close to scientific break even. Haven't quite gotten there yet. But there are clear hurdles and metrics to which we're pushing toward. At the bottom here, I highlight where we really need investment is looking at our driver technologies, in particular the efficiency of lasers, different kinds of lasers, whether it's solid state diode pumped, excimer, pulse power is another type of inertial energy concepts for fusion. So there's a whole trade space here where improving the electrical efficiency will be critical so that we can boost our gain, right? And same thing on the MFE side, moving toward that. And the value proposition, again, I show sort of a sort of toy model here of what that pilot plant could look like. And the key is that we can't be one and done once a day. This is at a rep rate, right? So pushing towards higher rep rate is really critical so that we boost that efficiency. Just for the sake of time, I highlight what we need to do, right? We got to get it hot. We got to do it quickly in a billionth of a second, over and over again. So at a very high rep rate. And we need the fuel. And that's where our science in the Rise Hub, my science in particular here at SLAC, where we are really focused on optimization of that material used to house the fusion fuel. But we can't do it alone. We definitely want to highlight the utility of AI. And there are many different aspects of the whole power plant ecosystem where AI could be overlaid in terms of driver technologies, how we're beating down the uncertainties in our physics predictions, right? The models that are used require these benchmark data that we're pushing forward. The kinds of target technologies and delivering targets at an appropriate rep rate, but still with the qualities and characteristics that are critical so that we do get that ignition. And then power systems across the board. I didn't even mention the aspects of the fuel cycle, right? So that deuterium, tritium, how we extract now that we've bred tritium, let's say, using lithium in our blanket and so forth, or molten salt. How do we then extract the tritium and get it back into our pellets, right? There's a whole fuel cycle aspect that's critical. But my value proposition to you all today is that with AI, with artificial intelligence across the IFE ecosystem, we can really obtain our superpowers. So I really like the Avengers, or think of I know He-Man is coming out, a new movie. But anyway, there's an opportunity here to really get superpowers in the fusion ecosystem, and in particular for IFE. And I think there's sort of four critical areas: designing better fuel pellets, understanding how to optimize that, the control systems, understanding that we humans are not going to be fast enough and we need more efficient control of our diagnostics, in particular for tracking of the targets for inertial fusion. Many of the materials we're going to use in our power plant, boy, do we need to optimize those. I don't even think there's really a scalable material that can withstand the 14 MeV neutrons, right? There are ideas, tungsten, there are a lot of innovative alloys that are being used, but our studies are right now still on the coupon scale, right? And so understanding what it will take also from a supply chain and manufacturing standpoint. Let's be doing our due diligence in exercising those issues. And then, of course, operating the plant in sort of a 24/7 timeline. And so here, for those of us who are sort of in the weeds and actually thinking about the critical technologies and the physics, I list out, where we need to be focusing as a community, both on the driver and laser technology, in particular for laser-based IFE. I know there are different kinds of inertial fusion concepts, but um, the coupling of the target, so laser matter interactions, really optimizing that, realizing that we are in a high rep rate paradigm. That means not just data, the high rate data consumption, but making predictions and decisions in real time for the next shot that happens in a tenth of a second. Aspects of the laser technology itself that need to be at a price point that they're just not today. So, how do we need to innovate in materials and coatings for these drive lasers? Um, Looking at full holistic models, sort of cradle to grave in terms of performance of each fuel pellet. And again, I will say that AI is a benefit, but you need that benchmark data. And we're not quite there yet with autonomous laboratories, right? So many of us who work together, we go to the light sources, we put the sample in, we collect the data, we're on our computers, right? So we're not there where there's robotics well enough or instrumentation control to execute those experiments autonomously. And I just sit in my office or drink my hot coffee or something, right? We still need humans in the loop, in particular for collecting benchmark data. Um, and then I won't belabor the point, but lots of good areas on the physics side and design work that can leverage our existing simulation capabilities, but certainly a boost there. And so here enters the Genesis platform. And so this is what I mentioned earlier on in the talk, that this is a new initiative. And we've put forward these proposals, and we're leveraging not just this agentic AI, but different ways of applying the AI overlay. I will say that a critical part that I've mentioned is really in extracting benchmark data from experiments and providing that unique data back into this AI architecture or ecosystem. And the key that we need in the community are really facilities and IFE demonstrators. And maybe at some point they will all be run by robots because of the harsh conditions and so forth. But we're not quite there yet, right? And so still having humans in the loop is critical. And that's where we here at SLAC are pushing forward aspects of our science and technology, in particular my division here. I'm deputy director with Professor Siegfried Glenzer, who's our director of the High Energy Density Sciences Division. And we have three main thrust areas of our portfolio, but certainly in particular is advancing inertial fusion energy. And we think about this overlay of the kinds of experiments and studies we need to do to address all the different areas you see here in this figure, many different kinds of measurements we need to be making at the appropriate conditions, from understanding the fuel. This is again leveraging sort of the NIF ignition success as our starting place or a point design for successful power plant concept. But so many different diagnostics and measurements that need to be made. At the heart of it, and what is really clear in my mind is that the starting place here is the target, is the fuel, right? Because without that, you will not get fusion. And a friend, a colleague of mine said, Arianna, come on, that's crazy. We're going to get to the place with our laser technologies that it won't matter what you put in the beam. You could put your shoe in there and generate fusion, right? And I think there's a trade space though. Certainly we will get advancements in laser technology, bigger lasers, more powerful lasers. However, the trade space of cost, right? What does it cost to operate some larger and larger scale laser system? I think it will eventually be cost prohibitive, and you'll still realize that, oh, we really need to hone our skills in designing and understanding the behavior of the fuel itself. And so here enters in much of our work at SLAC and with the RISE team in what we refer to as our Thrust 4 with Professor Richard Sandberg and colleagues at CSU, Professor Jorge Roca, and others in looking at the materials properties of the capsules. And the capsules really are a marvel because what we saw to be successful on the NIF required incredible precision and care and cost, right? So if a pellet capsule on the NIF is something like millions of dollars, we can't have that price point for a commercial fusion concept. We need it to be something like 2 to 3 pennies per capsule. So that's a big cost difference. And so how do we do that, meet the cost requirement, but then also optimize the performance characteristics? Because we realized on the NIF with the success, we needed a perfectly spherical implosion, which required perfection in the capsule material itself. And so here I show a cartoon version of sort of what is notionally required, but there are always blemishes, imperfections, roughness, voids, you name it. That's what's going to come out of essentially high volume production manufactured materials. And we know from our physics models that that's a problem, right? We see that instabilities form when you try to compress something that has these imperfections. So the symmetry that is so key here cannot be mastered if we don't have appropriate materials. So here's another space where AI can help us understand what that physics outlook and tailoring experiments can do in sort of the design of our capsules or other, I didn't mention it here, direct drive versus indirect drive, and this notion of a whole ROM or a half ROM, the shape that's appropriate, how to get the most bang for your buck, and then not just designing these targets and testing them, but then also delivering them at a high rep rate, not just delivering them once a day, but once a second, and then able to track them on their little journey of the chamber. So I think there are a number of ways where AI will eventually, or is clearly being recognized as critical in many commercial and private industry paradigms, where we have to do this sort of inverse design. Start where we know we need to end up here. Let's work backwards. How are we doing that precision fabrication? Understanding on that little life cycle of the target, how are we tracking characteristics? Is this a good target to shoot as it's traveling through? Does it have some flaw? And then the holistic mapping of the entire power plant in sort of a digital twin. And so we can pull from a lot of new capabilities in AI and the sort of autonomous experimentation research engine. I think this is a direction we want to go. I would say right now, many of the national labs, academia, maybe even commercial, are looking at each of these areas individually. And the Genesis platform is considered a way to try to bring all of the components together. We've done our due diligence, we think, or are doing within the RISE Hub, leveraging a lot of the fantastic facilities and networks to go collect these data across the US and internationally. And in particular, here at SLAC, and also to the workshop I highlighted earlier, I use the LINAC coherent light source, which facilitates aspects of the matter in extreme conditions end station. So for those of you who don't know or haven't been here, please always feel free to reach out to me if you're ever in the area, give you a tour. But the LINAC coherent light source is this phenomenal camera, essentially. It's a camera that gives you atomic scale resolution with a shutter speed that's shorter than a phonon period. So what do I mean by that? Femtosecond, and I'll just play this little video here. Femtosecond temporal resolution. So as your materials are undergoing some dynamic process, the snapshots we are taking are a true freeze frame of the atoms in their various positions as they undergo. a transformation. And what happens here at the LCLS is you accelerate these electrons and pass them. The secret sauce is that the acceleration distance over which we're able to do this and have a series of magnets of alternating orientation is over 2 kilometers. And these different magnets that are blue and green that you just saw, because of right hand rule, right, we're making the oscillation, the synchrotron radiation that is generated has to switch point to point, magnet to magnet, and you end up extracting X-rays that are actually uniquely in phase and very bright. So there's the namesake, an X-ray free electron laser. So we're generating X-rays with laser-like properties because of these magnets, these undulators that are so close together, and we're able to tune their periods. There's a lot of innovation going into leveraging these exquisite facilities, like I mentioned, the LCLS, for studying aspects of fusion capsules and their materials. And what's really come out in recent studies is the utility of these nanofoams to hold liquid deuterium tritium fuel is key. But we're still putting forward many innovative and exciting experiments that help to understand how we mitigate issues of instabilities. And so lots of fun. I should say, shout out to many of our collaborators and colleagues who've participated in these experiments. So I'll just jump ahead. I think what I wanted to get to is here AI is really going to enhance our capability across the board in fusion. I am excited to share this message with you and hope you see that you, as early career students, thinking about your future careers, that maybe you see yourself in this ecosystem in bringing star power to the earth. I also want to highlight again, I will skip over many slides, that here at SLAC, we're going to be hosting this workshop in August. If you're able to join, that would be fantastic. Please feel free to reach out to me for additional information. And this is my last slide. Okay. Fusion is a race, right? We can see our path forward to bringing energy to the grid using fusion by at least 2040, certainly a power plant in the 2030s. And that's not that far away, folks, right? We're already 2026. So incredible opportunities. There's a QR code here up at the top if you're interested in getting more information about the RISE Hub and the US IFE portfolio. Please feel free to reach out. And with that, I will take any questions. Thank you so much.
Thank you so much. I would like to invite everyone to give a round of applause for this insightful talk by Dr. Gleason. Fantastic job, Ari. Thank you so much for your time. I'm just gonna quickly transition into the questions that we received. Levi Hancock from BYU, he asked that this question with currently in the world that there is ever increasing stress across all industries that we will lose our job to AI. Considering this, what skills can we develop as young scientists that will make us irreplaceable by AI?
Yes, what a fantastic question. Thanks for that. I think this also resonated at the National Science Bowl with all of these 800 high school and middle school students who sort of asked a similar question. And I think really the hands-on requirement of orchestrating experiments that provide benchmark data for any kind of code or simulation, not just in fusion, but in physics, in astronomy, in chemistry, in biology. There are still there's still so much garbage in, garbage out for many of these. In the large language model paradigm, certainly, but even as AI agents become more sophisticated, right? It is true. I think there's some statistic where 3 years worth of a student can be sort of completed in something like 3 days using agentic AI, right? But that is in a paradigm where you maybe don't need, to do experiments. And so here I think critical aspects, critical thinking, having that physics insight that comes from perhaps hands-on learning. My bias is certainly experiments. I think that the future will be, autonomous labs, but a human in the loop to understand and verify calibrations, performance, and actually do the data collection in the near term and the long term. That's a space where it's never going to go out of style. You will always have job security. Thank you. Yeah, great question.
Yeah, thank you for your response. We have another question from BYU audience. They ask, though, how the fusion chamber is going to maintain its laser precision with multiple reactions happening back to back is still a question of mine. The incredible precision required for the first fusion reaction is proven, but can it be reliably repeated without intermittent resets of equipment?
Yes, that is a that's a fantastic question, and I
It's a
think
really hard question.
it's a very hard question. Well, so even right now, as we see companies, designing in sort of a modular way, how the integration of the target and the driver and the monitoring of performance of each of those, and then the engagement. And I think it comes down to ensuring we have real-time, appropriate diagnostics that are constantly monitored. And the reset time, that sort of also depends on aspects of the specific concept, the type of laser used, the geometry, how many beams have to be coincident, the structural, the size and length scale. And I think a lot of these things, it's sort of the answer is like it depends. But to the first order, we are also building diagnostics, cameras, detectors with ever innovative materials that are radiation certainly rad hard, resilient, but still have a latency or a response time that is rapid enough so that we're getting information off of that diagnostic to some system to make a decision. So to the point, to the question of controls, I think we're going to get there. The innovation in the microelectronics and sensor space is also at parity with where the needs are and recognition of the needs for future fusion reactors. So that's good news, right? On the turnover, when aspects of the chamber need to be swapped out, and how do we do that efficiently and effectively? I think that's where robotics and maybe AI enhanced robotics that's already being also worked on right now. That's going to play a role. It'll still take time, and I will say it's likely concept dependent. But yeah, great question.
All right, thank you so much for that. I also have a question myself. With the dilemma of AI accountability, can you comment on the like decision-making process and the fact that who will like take responsibility for the outcome of the decisions that AI makes with,
Yeah.
all the intricacies involved?
Yeah. So that's a great question. It almost borders sort of on a philosophical question. And this came up too. The high school students were asking one question quite in a pointed way, will AI take over and then will we all die, right? It was sort of the direction, right? So to your point of accountability, and I think at this point, it really is our ability to harness AI as a tool in our toolkit. But at this point, don't be dissuaded or saddened. It really is take it as an opportunity so that we can be thinking about these big picture opportunities and advancements. And it is still very much in our control. But maybe to your point of who's doing the checking, right? We, the scientific community, have to do our due diligence. And again, that goes back to appropriate experimentation, collecting the data, having a human in the loop, being able to readily interpret the results, right? And do the fact checking. And that will persist, right? So I think it's a tremendous opportunity to have, augmented production. Think of it as the next industrial age, right? We are in the fusion age. We are in the AI age. And those two things together are remarkable. And so it really is an incredible opportunity for a bright future.
Yep. Thank you for your response. For our last question,
Yep.
we have this question that asks, for fusion, AI has many different arms to be trained. Which one is most important, target fabrication or laser driver?
Oh, wow. Look, this is a question. I would say, okay. So my bias, of course, I'm come from a more material science background. My opinion is that the capsules and the materials are the most important. I think there's a lot that needs to be done still on the experimentation side to benchmark and validate many of our physics models. However, on the other side, got to have the laser technology or the driver technology. So I think the need is actually, it depends on who you talk to. Okay, so I'm going to say it's on the target side. Somebody's going to email me and tell me no, but I think the targets are so critical. Lasers will, of course, get bigger, faster, stronger. Yes. Will they be as cost effective? That's a great question. I think that depends on materials innovation, laser technology innovation, which is also advancing. So I think actually the need is equivalent on both sides, but because I'm an experimentalist working on targets, I'm going to say targets.
Right. That's an arguable response, but we'll move forward. There were a couple of other questions which I believe you kind of responded to them throughout your talk. Uh, I'm just gonna read the question. This was from BYU audience.
Mhm.
Uh, they asked, how would we be able to harness inertial fusion energy? It seems comparable to a lightning strike, fast and powerful, but too brief to harness at the steady supply rate the grid needs.
That's a great point. So that's where the rep rate comes in. We have to, right. So one given fusion reaction will generate some amount of heat, and that heat is then absorbed by the wall, the first wall, and the blanket construction. But you have to then supply the next reaction, right? So you have to sustain and keep that high temperature over a longer period of time. So you keep the requisite temperature of what you're supplying essentially to the heat exchange conversion to boil the water and spin the turbines. And so that requires, that's where this requisite repetition rate of around a hertz, a few hertz to a fraction of a hertz, is in the minds of many IFE fusioneers. And if we don't sustain that, right, if you get too slow, then you're exactly right. The temperature of your wall and then your heat exchanger is not as efficient. You're not supplying enough heat to boil the water and spin the turbine. So many companies have worked backwards to determine, well, what is that rate given my driver technology?